Hello, I'm Pierre. I'm a security analyst at eShard, which is a security company based in France. And I'll present to you a study that we made. Is the ARM TrustZone attackable by Rowhammer? Don't worry, the presentation contains an introduction of both technologies, and we'll shortly also describe the attack. So more or less 25 minutes. So what is Rowhammer? It's an attack technique that's used to corrupt RAM that's been around for a few years. What is TrustZone? It's a security technology that's in most ARM processors nowadays, and we'll use Rowhammer in order to target the TrustZone implementation in a system. This TrustZone is in every smartphone that we use nowadays, Android-based smartphones, so it's a bit ubiquitous. So first, a bit of context. There's been Rowhammer has been around for a few years, and there's been multiple implementations on PCs, on mobiles, and every time the usage of it is to gain more privileges, like root privileges from a user program. This study is not about this, it's about targeting a secure OS from Linux, so it's a bit different. What about TrustZone? Do we have attacks about it? Yes, most of the time it's software bugs in the secure OS, which allows you to take control over it. And very recently there's a bit similar attack that went out that uses faults generated by scaling, power scaling, etc., to create faults in the microarchitecture. So it's a bit similar. What's the attack about? So we have on our system a Linux kernel or Linux system, and next to it there's a secure OS that's running. On most Qualcomm smartphones, it's Qualcomm Secure OS, for example. In our case, for our proof of concept, it's a secure OS that we derived from an open source project, and that we attacked from a Linux system. What's the objective? We want to corrupt memory in the secure system, which is normally impossible. And if possible, exploit these faults in order to gain more privileges or retrieve secure keys, etc. We don't care about routing the system, so the aim of the attack is to attack the secure side from the non-secure side, so we take directly full privileges in the non-secure side. So we are a kernel module if we want. So this is the POC that we made. We have, as I said, a Linux system, and we have a TEE, trusted environment, that provides a signature mechanism to the Linux side, which is quite common in smartphones. You have the keymaster thing, which you can use from Android. And we'll use Rowhammer in order to fault some keys in the secure region of memory. And then this will allow us to retrieve private keys using a well-known crypto attack, which is the Belcore attack, if you're familiar with it. So this is the picture of it. You have a Linux program here. You're asking the TE, the trusted OS, to sign a message for you. The secure system will use some keys that are stored in its private space, in the secure space, and then it will return a signature on the public key. What we'll do is we'll do a Rowhammer attack on the memory. It will corrupt some parameters in the keys here. Because of that, the signature will be faulty. It will compute a C prime signature instead of a normal one. And we'll get a corrupted, faulty signature, and that will allow us to retrieve the private key using the Belcore mechanism. About Rowhammer, a small introduction about Rowhammer. What we want to do is corrupt things in the DRAM chips, and we are executing code here. And there are several elements that prevent us from directly accessing the RAM. There are the caches, the DRAM controllers that have some optimization logics, etc. And what we need to do is do lots of accesses so that will corrupt memory cells. So you have to know the layout of the DRAM cells, etc. That's the biggest issue. The caches are the biggest issues. So to understand how to implement such a system, we need to understand how RAM works. So every bit of RAM is stored as in a capacitor, and when it's charged, it means it's 1, and when it's discharged, it's a 0. The capacitors can lose charge over time, so they need to be recharged over time. Also, if you read a bit of memory, it will be discharged and then recharged to preserve its value. All these DRAM chips is made of multiple banks, usually 8 banks. Each bank is organized in arrays, usually, for example, 8 arrays here. And then each array is a grid of capacitor. It's a simplification, but it looks like this. And when you want to read a bit of memory, you have to do it row by row. So what happens? You have an address that you want to read. The CPU drives some things. It goes to the DRAM controller, and the address arrives at the DRAM controller. The most significant bits are gives you which row to access, and then the least significant bits let you select some bits. So there's only a few operations that you can do on rows. You can activate a row. That means that all capacitors will be discharged and read to a row buffer, and then you get your data out and it goes back to the CPU. The thing is, if you access a row, if you activate a row several times in a row, that's called Rowhammer, and it will probably disrupt the cells that are nearby. So if you access, the issue is if you access a row, let's say row 2, several times consecutively, you will hit the row buffer, and you won't activate the same row a lot of times. So what you need to do in order to create faults is accessing 2 distinct rows in a single array. And that will do things like that. So for example, we access row 1, row 4, row 1, row 4 in a loop. What do we get? We may generate some faults. So maybe this bit goes from 0 to 1 or 1 to 0, and that's bad. One thing which is interesting, it's if you access 2 rows, if you want to target a row n, the most efficient way is to hammer to access consecutively row n minus 1 and n plus 1. It's a kind of combo attack. So the problem we have is how do we address rows from the CPU, because all we have is addresses, and we don't even know about rows normally. So we need to determine the physical properties of the DRAM. Usually, so you have something like that, and you would think that consecutive access will access consecutive rows, but it's most of the time not the case for bandwidth reason. Usually when you access consecutive addresses, it will go from one bank to another, so that when you don't need to deactivate this row in order to access this one, etc. So it maximizes the bandwidth. So we need to know how many banks there is, the width of a row, etc. And it's all variable. It depends on which DRAM chip you use. So you can read the data sheet if you have it, or if you can determine which DRAM you have. But one thing you can do is use a timing characterization. We use that and it gives good results, and it lets you deduce the number of banks and also the size of a row. What you know is that accessing two distinct rows in a single array is slow because the first row has to be refreshed before activating the second one, etc. So if you have, if you take a base address and then access all addresses which are nearby, you will realize that sometimes it's slow, and it means that you are in the same bank and the same array. So, for example, in this case, we had a DRAM which had 8Ks of width, and this DRAM chip used 8 banks. Once you have that, you know how to access rows, but how to bypass the caches, etc. In most implementations of Rowhammer, the issue is to bypass the cache using techniques like cache eviction, etc. But since we are in kernel space, we don't have this issue. Since we are kernel, we can decide which attributes our memory mapping uses. So that's something the kernel does all the time in order to access devices, like, for example, a timer. If you have a timer that provides a memory mapped value of the time, you don't want it to be cached. You want to read the real value of time, and that's why memory attributes exist. So we can do that for the RAM. That's an advantage because we are in kernel space and targeting the secure OS. So that's easy. The algorithm of Rowhammer is pretty simple. You just access the rows. And what happens after this loop, a number of iterations, some bits around the row before and row after will be corrupted if the device is vulnerable. What about TrustZone? So what is TrustZone? It's a security technology that's built into all Cortex-A processor that we have in smartphones. And yeah, that's the equivalent of having a separate secure processor, but we don't have to buy, the system integrators don't want to have two processors because it's too costly. It uses silicon space, etc. So it's okay. The basics of it is you have a processor and you are time sharing it between the non-secure side and the secure side. So you have two OS running, one which is Linux usually and one which is a proprietary secure OS. And you can go like time sharing between two user processes. You are scheduling one OS or the other. How does this work? So the CPU can operate in two modes, secure or non-secure. On every memory operation is marked with the state in which the processor was when the read was made or the write was made. So for example, we are running an Android application. It's in non-secure state. So every read that goes to the DRAM controller is marked as NS, non-secure. And if we are running in the secure state, then it will be marked S, which is secure. And then the DRAM controller needs to be aware of this flag, and if it wants, it can block some operations that it feels are not legal. So usually you have a part of DRAM that is reserved for the secure OS, and let's say from 0 to a value, and for example, if it sees that, it will just return an error. So if you have your smartphone and you're trying to access the portion of memory that is reserved for the secure OS, you'll get an exception. As you can see, it's pretty flexible. Any IP block can be adapted to have some rules about security. It just has to interpret this flag. In our case, we are interested about the memory controller, and this is how it's implemented usually. You have, where is the CPU? Here. And you have a DRAM controller, And what you can do is modify your DRAM controller in order to have it for it to have rules about which portion is secure or insecure, or you can use a separate IP in front end which has these rules and acts a bit like a firewall. In terms of processor architecture, the CPU architecture was extended a bit so that you can have a secure state on a non-secure state. It looks like this. If you don't have TrustZone, you have only the black parts, and TrustZone duplicates this stuff and adds a new mode which acts as a bridge. So, for example, you are in an Android application here. You ask the standard key master to sign something for you. The processor will have to switch from, you will make a syscall to go to the Linux kernel. The Linux kernel knows it has to talk to an app that's running in secure side. So it will ask the monitor mode to switch to the secure side, and then the secure OS will be scheduled, etc. So it normally does an animation, but it looks like this. You can do things like that and then go back. During execution time, it looks like this. Your CPU boots normally with the bootloader, etc. in secure state. It will initialize its OS, then pass the hand to the Linux kernel, etc. And when Linux wants to ask something to the other side, it just does a context switch using the monitor. So we know how Rowhammer works, we know how TrustZone works. What is the attack? The attack is corrupting the secure processor memory. And an example exploitation is this signature attack. So this is the math about the signature RSA signature implementation. There is a well-known optimization of this calculation, which is the CRT implementation of an RSA signature. And it uses these parameters. I won't explain, you can find it on the internet. And what happens is if you corrupt one of these parameters, DQ, for example, then from the faulty signature that you got, you can deduce the private keys. So this is what we implemented. This is our implementation. We have a trusty secure OS, which uses some private keys. We have our Linux kernel here with the kernel module that's used to do the Rowhammer attack on the trusty OS. And we have the calculations about the GCD, etc. in the user space tool. How the physical memory is split. So this is the whole 32-bit virtual memory view of the system from the CPU, for example. The DRAM is mapped at this physical address. And here in red, we can see the parts which are reserved for marked as secure by the DRAM controller. What Linux can access is only the red parts. So we'll do a Rowhammer attack on the border of the memory regions, and it will corrupt some bits here in the keys, and that will let us retrieve the private keys. So this is how it happens. We have this user space tool which has a message, sends it to the trusted side. The trusted side generates a signature, and then the user space tool tries to compute the GCD that we just saw. If it's equal to n, then no faults have happened in the correct place, and we cannot retrieve the key. If we do our Rowhammer attack, so that's our way to communicate with the kernel module. For example, here we access these rows at these addresses, and that will probably generate faults in the nearby memory areas. We also have counters from the DRAM controller, which tells us how many reads per second we do, because that's the important thing about Rowhammer. If you can't do enough accesses per second, then your attack is not successful. This is a case where we used the Rowhammer attack. It corrupted the keys in the trusted side, and we got a faulty signature. And what does it give us? We can deduce a private factor, and if you have one, you have the whole private key. What happens if from the Linux side you try to access directly secure memory? You get this kind of exception we talked about. It's a kind of external abort. It's an exception that comes from the outside of the CPU. The conclusion is that TrustZone and things where we share some resources with when there's a non-secure, if you share things between non-secure and secure, there's probably a way that it can be attacked. So that's a proof that TrustZone is not perfect. The limitation of this attack is that you have to have critical things in the secure and non-secure border. And probably some current implementations that you have in smartphones can be attacked this way. And the mitigation is simple. You just have to not put critical things near the border. And this is an ad from our company. We have a few internships positions. Questions, and I also have a recording of a demo, if maybe.
Oh, we can look at the demo and take question after.
Okay. It's anyway, it's just a terminal. So it looks like this. You have the okay.
Black box demo.
Okay, you just have a kernel booting. I think it's useless. Some stuff there, but it's not very important. I need to scroll, but it's just what you saw actually. There's nothing much to see. So what happens? You need to use we use our module. It does some init. What we'll do is try to get a signature. Because no faults have happened, we can't get the private factor. Now we are trying to do the Rowhammer attack. So it takes some time in order to access memory. We're trying to sign something. We get a faulty signature and we find the private factor. We can ask the trusted side to regenerate a pair of key and observe that, oh no, that's not what we do. We try to access secure memory. So that's the kind of thing you get, a kernel exception. And if you try to regenerate a pair of key, then it's not faulted, so you won't. It's a bit a demonstration that it's not fake. You have to really to do the Rowhammer stuff to get the private key. That's all.
Okay, thank you very much.
Thank you.
We have time for some questions, comments. Yes, sorry.
Hi, thank you very much for your presentation.
Thank you.
I think it's somewhat quite clear for me how you managed to do a fault on one row. What happens if you have several faults, especially if you have two faults, well, one fault in each sub-exponent in RSA?
So for example, if you fault DP on DQ, it doesn't work because that's how the bulker attack works. But you may have luck and sometimes fault only a parameter. You can do, unless the system is protected by some you can only do a few signatures and then you can't anymore. But it's it's luck. You can, you try until you fold the correct stuff. It's a bit random.
Okay, other question? Comments? I have a question. How long does it take to mount such kind of attack? You spend 2 days, 1 year, 3 years? I don't have any idea.
We were already interested in TrustZone before doing this study, so it took us maybe three months. It went a bit fast. We thought it would take more time, but yeah, it can take a long time. Sometimes you have.
And how do you have the intuition that it will work? Because you never know.
Because there's Rowhammer that's working on the system, and there's no reason why there's no countermeasure for it, so it must work. That's.
Okay, do you have an idea about the countermeasure?
Yes, you just don't put critical stuff near within the reach of Rowhammer.
So thank you again, and be quiet after. Thanks again, the speaker. We have some announcement about the general chair. Thanks again.